carbon dioxide was being stored as biomass, as their little plant and animal bodies, and some of it was turned into limestone, like this stromatolite fossil here. So as we move up through geologic time, we've always had oxygen, and as a result, we've always been sequestering at least a little bit of the carbon dioxide that was in the Earth's atmosphere. So for an oxygen record at Grand Canyon, if we've always had oxygen in the air at Grand Canyon, there's really not a whole lot of a story to tell here. We do know, though, that it has increased. From our oldest rocks, a little over 1 billion years ago, down here, the Hakati Shale being an excellent example, 1.2 billion years old, oxygen was present in the atmosphere, only about 1 to 10% of its current amount, but free oxygen in the air. By the time we get up into the layer cake geology of the canyon, those familiar horizontal rock layers, oxygen was at least 3/4 of its current level. So oxygen has been around for most of the, or for all of the history of the Grand Canyon. Changes in oxygen level in the atmosphere have probably influenced the evolution of different creatures that have lived on the Earth, but they haven't had a huge impact on climate. Climate changes have mostly been the result of changes in carbon dioxide. Well, now, carbon dioxide levels have also changed through geologic time. What we're looking at here is the record, the amount of carbon dioxide in the Earth's atmosphere as it has changed through time. Sometimes lots and lots of carbon dioxide, sometimes not very much carbon dioxide. And what you can't see down here, because this chart is done in millions of years, going back 600 million years, what you can't see is the little spike down here at the end that goes up to about here. So what we're looking at is the carbon dioxide level of the atmosphere when all of these rock layers were being formed. Now, if carbon dioxide is an important greenhouse gas, we might expect that the Earth was warmer when there was lots of carbon dioxide and colder when there wasn't much carbon dioxide. And lo and behold, if we take a look at oxygen isotopes, which are the red line here with the margin of error here and the long-term rolling average here, you can't get enough of these statistics. There's just nothing like them. Excel has so many, but anyway. What you can see is that there is, if we look at this oxygen isotope thermometer when the Earth was warmer, colder, warmer, colder, there's not a one-for-one relationship, but we do find a relationship. Times when temperatures were cold, carbon dioxide levels tend to be low. Times when temperatures were warm, carbon dioxide levels tend to be high. High, warm. High, warm. Low, cold. These blue bars here at the bottom are where it's really cold. These dark blue bars are ice ages in the Earth's past. And as we move on into Grand Canyon's history, we do find evidence of ice ages. Now, I mentioned before that oxygen's always been around. Life has always been around during Grand Canyon's time as well. Simple life in the beginning, single-celled bacteria-like creatures living down there. We don't find fossils in those oldest rocks because 1 3/4 billion years ago, we went through a period of mountain building. These rocks were squished. You can see the nice even layering in these rocks is gone. They've been intruded by molten material. They've been folded in half, buckled, twisted like saltwater taffy. Any fossils that our oldest rocks may have contained were completely destroyed. So we actually have to go elsewhere in the world to find fossils in rocks as old as the oldest rocks at Grand Canyon. But when we go to those other places around the world, we do find fossils. So there was life on the Earth then. And then our oldest fossil record of, our oldest fossils in the Grand Canyon show up a little over 1 billion years ago in our tilted supergroup rocks. And that was right about the time that nucleated cells, like amoeba and that kind of stuff, really show up in the fossil record and started taking off. Well now, for whatever reason, maybe it was the appearance of those nucleated cells, what we call eukaryotes, for those of you who managed to successfully complete your Bachelor of Science in Biology. But those nucleated cells and life in general became much, much more abundant about 600 to 600 to 1,000 million years ago, about around a billion years ago. A lot more life living in the sea. A lot more creatures dying in the sea. And their little corpses, microscopic though they were, began to accumulate on the sea floor. They were deep enough down that some of them didn't decay. They became incorporated into the rock. And so we had these creatures taking carbon that had once been carbon dioxide in the atmosphere and turning it into black layers of shale at the bottom of the ocean, taking it out of circulation, putting it into that geochemical cycle, locking carbon dioxide away in the rocks. Carbon dioxide levels started to fall in the Earth's atmosphere. Ice caps started to form near the poles. And at that time, about a billion years ago, the arrangement of the continents was such that the ice caps in the poles just kept getting bigger and bigger and bigger. There weren't any land masses up there to interfere with them. And under some hypotheses, as those polar ice caps grew, they started to reflect more and more of the sun's warmth back into space. I mean, bright white snow reflects a lot of light. And so consequently, the Earth got colder. So the ice caps got bigger. They reflected more light. The Earth got colder, the ice caps got bigger, reflected more light. The Earth got colder, the ice caps got bigger. And the Earth spiraled out of control into a situation that has been called Snowball Earth, where glaciers covered the entire planet, pole to equator, land and sea. We were just a frozen ball hanging in space. Now, I'll tell you right now, this is a hypothesis. See this question mark here? That's a very important question mark, because there's a lot of geologists who don't buy this. They say, okay, we freeze the Earth solid, cover it with ice, and everything's still alive after the ice melts. How does that work? And so there's some question as to whether the entire globe really froze, or maybe we had just kind of like a slush ball Earth, or something like that. But regardless of how much, we do know that the Earth went through a tremendously cold period. And the glaciers, if they didn't completely cover the Earth, came pretty darn close. We find evidence of glaciers clear down along the equator. And it wasn't until the geochemical carbon cycle, specifically volcanoes, had pumped enough carbon dioxide back into the atmosphere that the Snowball Earth thawed back out again.
This is pretty cool.
Yeah. Yep. Yeah, about 700 million years ago. So the Earth thawed back out again, and we get up to one of Grand Canyon's more famous features, the Great Unconformity. The layer, or the base of the horizontal rock layers that make up the upper walls of the Grand Canyon, resting on top of the basement rocks. These basement rocks, I mentioned, folded, twisted, mangled during mountain building. Those mountains had all eroded away, perhaps partially because of the glaciers during the Snowball Earth hypothesis, if that's correct. They had eroded away down to a smooth plain, and then horizontal rock layers started to deposit on top of them. So here we see the vertically squeezed basement rocks in contact with those horizontal rock layers up above. The line separating them represents 1.2 billion years of erosion to remove that mountain range, erode it down close to sea level so that beach sand could be deposited on top of it. Well, now, if we look closely at this Great Unconformity in this close-up shot here, we can see that the upper part of those basement rocks is not looking very rocky. In fact, it looks pretty rotten. It was deeply weathered. It was well on its way to becoming soil. Soil formation, in some cases, that extended more than 50 feet below the surface of the Earth. By the time these rock layers were forming in the Cambrian period, about 525 million years ago, carbon dioxide levels had rebounded. In fact, they were higher probably than what we have today. So high carbon dioxide levels. High carbon dioxide levels mean that rain falling through the air is going to pick up that carbon dioxide and make a weak acid, carbonic acid, the same stuff that dissolves away caves in limestone layers today. So high carbon dioxide means more carbonic acid. More carbonic acid means more weathering, and that's why we can find a zone of weathering up to 50 feet thick.